Alright, so we're going to come back and we're going to look at gravity in a different way. And so basically up until now we've always dealt with the gravitational force as the force the Earth exerts on anything pulling it down towards the center of the Earth. And all we're going to do is say that, well, gravity can be, the universal law of gravitation tells us that there's a gravitational force between any two particles that have mass. And so if you want to think about that gravitational force, so take two particles, so here's mass 1, here's mass 2, and if you separate those two masses by a distance r, then that force has the following properties. One, it's directed along the line joining the two particles. So notice here we're basically drawing two free body diagrams. So this is the free body diagram for mass 1, and mass 1 feels a force exerted by mass 2. So mass 1 is gravitationally attracted towards mass 2. Mass 2, here's its free body diagram, is gravitationally attracted towards mass 1. So both of these forces are directed along the line joining the two particles. Both of these forces are attractive. So gravitational forces are always attractive. In dealing with the gravitational force up till now, the reason that we've always said that it points down is because you are always being attracted towards the center of the Earth. And then 3 is it has a magnitude given by this expression. So big G is known as the gravitational constant, and it's 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And you can think of this as basically it's a conversion that takes a product of masses divided by a distance squared and turns it into a force. So mass times mass gives you kilograms squared, that's going to cancel that out. Distance squared gives you meters squared, that's going to cancel that out, and so you're just going to be left with newtons. So what the gravitational force cares about is a product of the masses. So it cares about both masses involved in your gravitational attraction and the distance that separates them. So we know that all forces are interaction between two objects, and the nice thing about this particular way of thinking about the gravitational force is it makes it explicit that the gravitational force is an interaction between two objects, and in particular two masses. So gravitational force cares about mass. You can think about this as basically what it's telling us is that objects feel a gravitational force because they have mass. So this is known as the gravitational property of mass. We talked about the inertial property of mass, the idea that to accelerate something that has a large mass, you have to give it a very large force. But this is the gravitational property of mass. And so basically it says objects that have mass feel and exert gravitational forces. Again, this tells us that the larger the distance between the two objects, the weaker the gravitational interaction is between them. So notice if I take my distance here, so the distance between masses 1 and 2, and I double it, well, that factor of 2 is going to get squared, which means that the gravitational force will be 1/4 its initial value. So the larger you make the distance between them, the smaller the gravitational force becomes. That's known as an inverse square law when it has this particular form. Right? So when it drops off in this special way of basically 1 over r squared, that's called an inverse square law, and we'll see quite a few of those in 299, or in the second semester of the course. The next thing to add is that gravitational forces are really weak. And that's because this constant is really small, right? Think about this, 6.67 times 10 to the negative 11. Well, negative 11 basically says you're talking about something slightly bigger than a trillionth, right? Negative 12 would be 1 trillionth. So this is basically 66.7 number. It's incredibly tiny. Because it's so tiny, gravitational forces end up being very weak. So if you want to feel gravitational forces, you've actually got to have large masses. That's why the only gravitational force that matters for us is the gravitational force due to the Earth. The Earth is our closest large mass. And then the other thing is that all forces are vectors. And so when we think about this expression, gravitational forces must also be vectors. And so here, this is just a notational way of saying that the gravitational force lies along the line between my two masses. So this is just sort of confirming what we started with when we said that we know that the gravitational force has to lie along the line that connects our two masses. This is just a special way of notating that in vector terms. But the important thing is that if we've got multiple masses, then we're going to have multiple gravitational forces, and they must be summed as vectors. So at the end of the day, this is still a vector summation problem because we're still dealing with forces.